Hello friends, welcome to our channel Mirror Neuron, which means watch and learn. So let's answer the question, the difference between stochastic gradient descent and batch gradient descent. So first we will discuss the theory and then write some simple code in Python to demonstrate its implementation. We will also answer some critical observations around it. First, we need to understand the linear regression model with multiple features and the gradient descent of that. So a linear model, when we have multiple features, would look like this. So say for example you have your output variable, which is your predicted output, and this is equivalent to your model parameters m0, which is nothing but the intercept, plus m1 your feature 1, plus m2 your feature 2, and so on, right? And we have seen this several times. And also we have another thing called as loss function, which for this time being we'll use as mean squared error, which is nothing but summation over all the records that you have, your y original value minus your y predicted value whole square. Okay, now in order to find the best model parameters, your model parameters are your m1, m0, m2, and so on. So in order to find the best model parameters which will best fit the data, we need to take partial derivatives of the loss function with respect to each of these parameters, and the result can be stored in a vector form, also known as gradient vector, and typically is given by a delta symbol like this. Okay, and here we will say MSE of all the model parameters m. Okay, and the solution of that is something which will look like this. So you're basically taking the partial derivative with respect to each and every model parameter of your loss function. Okay, and that also we have seen in several occasions in our previous theory classes, right? And so on. So basically you'll do it for all the model parameters that you have. So if it is k parameters, then it will be like this. Okay, so this is your the gradient vector. And what is the solution of this one? So we know that in order to find the solution, we have to set all of them equal to 0, right? So basically we'll get that many number of linear equations which we need to solve. And we have also seen in our theoretical class that the solution of this one, when we have multiple features, okay, and the solution is very simple and straightforward. It looks like 2 over the number of records or the data that we have times the x transpose dot product with x dot the coefficients minus your original value. Okay, so this is your gradient. Now this actually gives you a some model parameters m. Okay, now what will be the next m? And that also we have seen. The new m is nothing but your m old or the old coefficients minus some learning rate times this above expression, which is 2 over n x transpose x dot m minus y. Okay, so this way you keep updating your model parameters. Now this implementation can be done in couple of ways. One is the stochastic method, one is the batch gradient method, and another is called as mini batch gradient. Mini batch gradient is something which we will look at it later, but right now my interview question is more about stochastic gradient versus batch gradient. So now let's try to implement this in Python code. But before we jump onto the Python code, let's create a small roadmap as we always do. Alright, so first we will look into the batch gradient descent, and then we will look into the stochastic gradient descent. Now before we write the code, we need to have few ingredients in place. The first is the learning rate. So I believe you already are familiar with what is the learning rate, right? So basically if your loss function looks something like this, say for example like this, and you have say m0 and m1, right? So in case of only one feature, so we have one intercept and one slope, but in other cases you can have a more than multiple dimension loss function where you have more features, so you will have more model parameters, m0, m1, m2 and so on. So those will be like in higher space. So once you have this three-dimensional thing here, so we want to find out this portion here, or the spot where this is minimized. Now in order to do that, we'll start somewhere here and then we'll gradually go down. Now this is called learning rate. Okay, so what should be your step size when you jump this way? So your step size could be small, your step size could be big. Okay, and we will gradually see what are the different implications that happens. Okay, now that is learning rate. Also, in order to come down here, we can keep running our code for like infinity amount of time, but that is not suitable for in the real world application. So basically we would like to know how many times I want to come down. So is it 1,000 times I want to do it, or is it 2,000 times, is it 10,000 times? It depends on the problem and also on our judgment and experience. Okay, so for the time being, we'll keep the learning rate eta as 0.1, a small value. So that means this step size is 0.1. Okay, and also we'll say n iterations, or number of times I want to do this is say 2,000 times. Okay, so basically I'm coming down, so I'll do it 2,000 times. Now here is two challenges. I might not be able to reach here within 2,000 times, so maybe I would later on change it to say 3,000 times. So I hope you are getting the point, right? All right, and then we have number of records or data point, which is in our example that we saw in our previous video is 100 records. We generated this equation, y is equal to 4 plus 3 times of x plus some noise, right? So this was our original data. Okay, so what I want to then do is, for this many number of iterations, for 2000 I want to do it 2000 times, and that is where I will like to first calculate the gradient. Okay, and then I will update my coefficients accordingly. So that is the basic algorithm here. Okay, so what will happen is I will iterate 2000 times, iteration equal to 2000, and for each of this iteration what I would like to do is first calculate the gradient, and we have already seen the formula of gradient, 2 over n x times your transpose dot xm minus y. But keep this in mind, this x has to have a column with all the ones. Okay, we have to do that processing as well, but that we can do directly here. And then once we have the gradient, we will update our coefficients like this, m by m minus learning rate times gradient, and that we have seen so many times in our theoretical classes as well. And once this 2000 iteration is complete, then we will get finally some model parameters which we hope will fit our data the best. Okay, so previously in our project we have seen that directly also we could have calculated, and we already have those parameters for m0 and m1, which was 4.45 something and 3.020 something. So let's see, with gradient descent can we find the same values. So let's write some Python code now. Okay, so what you can see here is the ETA defined is 0.1, which is the learning rate, and how many times should I update the model parameters is 2000. So typically what happens is our life would not be so easy, if the loss function was just a convex function, right, like a U-shaped curve, then life would have been so easy for us actually to get to the bottom, and we could have just keep repeating until we reach that bottom value. But in real life the loss function could be anything, maybe such an irregular shape. So that is why we have to be some judgmental about how many times should we be updating these model parameters. The number of sample or the records that we have is 100. So as we have seen in our code earlier, okay, if we go all the way up, so we have created a 100 record data set. Okay, so I'm just scrolling down. Okay, So the coefficient, again, in order to create your model or calculate your model parameters, we have to make sure that we start somewhere, and that is where we create a random initialization. And if you see here, I'm using the rand n function, and I'm passing two parameters here, 2 comma 1. So basically I'm creating two initialization. I'm basically creating two values, random values, and these two values are for m0 and m1. So basically for your intercept and for your slope. Okay, now I know I have to run this code for 2000 times, so I'm going for I in range n iterations. That means I'll be running this code for 2000 times, and what I'm doing is just solving the gradients by that formula that we have seen in the theoretical part of this question, and we are updating the m coefficients with that new value of the gradient using m coefficient minus eta, which is our eta, learning rate, times the gradients. And once it runs for 2000 times, we are getting that model parameters as 4.45 and 3.020, and this is exactly the same value which we calculated using the standard linear algebra formula, and you can see it's the same value, 4.45, 3.020, and so on. Now what are the simple observations that we can see from here is, while using batch gradient descent, we are actually taking the entire data set. Now imagine if we had a very large data set, and if we have to run 2000 times or even 3000 times or 5000 times, it is going to be extremely slow. So that is the first problem with your batch gradient descent method. Okay, that means running it for so long. And the second problem is trying to identify the learning rate. Here we have considered that the learning rate should be 0.1. What if I started with learning rate of 10? That means it is quite large. And what if I had started with a learning rate of 0.001 instead of 0.1? When the learning rate is small, what happens is it takes a even long time to come to the bottom, and probably it might not have reached the minimum within 2000 steps. Okay, that is the problem with your small learning rate. And if I had a large learning rate, the problem is I might overshoot my minimum and go even far away from my minimal point. So that is another challenge when we are not sure about the learning rate. So while we are going to do stochastic gradient descent, we will hope to make some improvement on this method. Not only we are going to reduce the number of training samples while we are updating these model parameters, so that way we are not taking the entire data set, and that is why it's called as stochastic. That means we are randomly going to pick some training samples or some training records. So instead of taking 100 records, what we are going to do is we are going to take one record at a time. So every time we learn or use our data set, we are only going to use one record at a time instead of these 100 records all the time. Okay, so that is the first meaning of stochastic gradient descent. Second, we will introduce something called as learning schedule. That means the learning rate will not be fixed all the time. It will keep updating, and we will see how to do that, because at different scenarios this learning rate should reduce gradually, not abruptly or not fast. Okay, so all those issues can be handled using stochastic gradient descent, and also we will see the cons of using stochastic gradient descent, and that is where mini batch gradient descent also comes into picture. Okay, so I hope you have understood how batch gradient descent works, and let's look into the next video how stochastic gradient descent would be in theory, as well as how to write a code around it.